Hello everyone, my name is Ozberk Dirik. Today I will presenting my term project for the intellectual mobile communication. The title of my project is Coverage Analysis of Downlink Satellites Network Effect of Shadowing. In this project, I modeled a low Earth orbit satellites network and analyzed how urban obstacles like building affect our internet connection quality. Here is sure is the outline of my representation. First, I will provide a brief motivation of why this topic is important. Then I will explain the system model of geometry we used. After that, I will describe the channel characteristic, which is the core of this study. Then I will walk you through the mathematical analysis where we derive the coverage probability. Finally, I will show the simulation result and conclude with the key takeaways. Okay, let's let's start with the introduction. As we all know, we are transition towards 6K, and satellite communication is becoming a key component of this feature. Specifically, low Earth orbit satellites are gaining huge attention because they offer much lower latency and higher data rates compared to traditional satellites. Companies like SpaceX are launching thousands of satellites to create mega constellations. However, there is a big problem in existing mathematical models. Most studies assume we are in an open field with no obstacles, but in reality, users are often in cities where buildings block signals. This is called shadowing. So, the main goal of this project is to fill this gap. I performed a coverage analysis that explicitly includes a realistic shadowing model to understand how urban blocks affect network performance. Now, let's look at the system model. Please focus on the figure on the screen. We model the Earth as a sphere with radius ρa. Satellites orbit at fixed altitude h, forming a larger concentric sphere. Instead of assuming fixed satellite positions, which is unrealistic for dynamic networks, we model the satellite's location as a random position point process. This allows us to use statistic tools to derive general performance metric. We perform our analysis for the typical user located at the North Pole. Due to curvature of the Earth, this user cannot see all satellites. They can only see satellites within the specific region, which we call the typical sphere cap, donated by A. Any satellites outside this cap is below the horizon and visible to us. Moving on the channel model. We don't use a simple path loss formula. We distinguish between the two propagation states. First is line of sight, where the user has a direct view of satellites. Second is non-line of sights, where the link is blocked by obstacles like buildings. The most critical part of model is the equation you see on the screen. P allows R is equal to exponential minus beta cotangent theta r. This equation tells us the probability of having a clear line of sight depends on elevation angle. If a satellite is directly above us, their probability is high. But as the satellites get closer to the horizon, the probability of blockage increases drastically. This realistic mimics a dense urban environment. To evaluate the networks, we use a metric called coverage probability. Simply put, this is the probability that our signal quality, specifically the signal to interference ratio, is above a certain threshold. The biggest challenge here is calculating the aggregate interference, since the number of satellites is random, and each satellite can be either blocked or unblocked. The interference is highly unpredictable. To solve this, I use scholastic geometry. I derive the Laplace transform of the interference, which you see method as lemma 1. This mathematical tool allows us to sum up the interference from all visible satellites by integrating over the spiral cap while accounting for the blockage probability of each individual satellites. Using the Laplace transform, I derive the final result, which is represented here as a theorem 1. Please look at the equation on the slide. This is an exact closed form expression for the coverage probability. Why is this formula important? Because it captures all system parameters. Lambda represents the satellite density. H is the altitude. And beta is blockage factor. This formula allows to predict the network's quality of service instantly without needing to run computer simulation for days. Now, let's prove that my formula works. In this figure, the solid red lines represent my analytic formula theorem 1, and the blue markers represent the Monte Carlo simulation result. As you see, they match perfectly. This validates that the mathematical derivation is correct. Also, please notice the difference between the triangles and circles. The triangle represent the strong satellites association, while the circle represents the nearest satellite association. The triangles are much higher. This provides that in a city connected to the nearest satellites is often a bad idea because it might be blocked a building. Connected to strong signal is always better. Next, let's analyze the effect of satellite density in figure 3. You might think more satellites are always better, right? But look at the top graph. It shows a curve that goes up and then down. This means there is an optimal density. If the density is too slow, left side, coverage drops. Why? Because adding too many satellites increase interference faster than it improves the signal quality. So, operators must find the sweet spot. Okay. Finally, figure 4 represents the most interesting intuitive finding of this project. Here, the x-axis is beta, which represents the density of buildings. Higher beta means more blockage. Look at the model. Look at the top panel of dense network. Surprisingly, as a blockage increase, the coverage probability improves. At first glance, this makes no sense. Why would obstacle be good? The reason is interference shielding. In a superdense network, interference signals from hundreds of the distant satellites effectively, while we maintain a strong connection to our receiving satellite. So, in mega constellations, urban shadowing actually helps by suppressing the noise. Okay, to conclude my presentation, in this project, I successfully model a LAO satellites network using stochastic geometry explicitly accounting for realistic shadowing effects. We derived exact formula and provide 2K insights. Optimal deployment operators shouldn't just float the sky with satellites. Density must be optimized. The dual role of shadowing while blockage hard signal strength. In dense network, its ability to surprise interference is actually more valuable, making to urban environments surprisingly favorable for coverage. This concludes my representation. And thank you very much for listening. Thank you.